Hello, welcome to the Transition Metals Workshop 1 answer video. Let's straighten that. Can we just... Yeah. Okay, what are we doing? We're doing Workshop 1. That's a W, don't even worry about it. Workshop 1 for Transition Metals. Yeah, that's okay. We're alright. First question was all about the spin-only formula for various complexes. This is more than we've done so far in lectures, but that's okay. You can supplement this with your own reading. We're going to have fun. So A is an ion complex. It is an octahedral ion complex. You know that the octahedral splitting is 2 above 3. And you know that ion 2 will have an electron count of the oxidation state subtracted from the group number. So iron is in group 8, we subtract the oxidation state of 2, and we get to 6 electrons. How do we fill those up? This is fun. The first 1, 2, 3 go as you would expect from your atomic orbital filling. For the fourth one you have a choice. This is something we're going to come to in more detail in later lectures. But there is a balance. So does it go in that first orbital again? Oh, look at this dotting. How beautiful. That's one place that electron could plausibly go. And the other place is up here. So does it get promoted into this higher energy set up there? What an interesting question. The answer depends upon a balance between two things. Thing number 1 is this energy gap. Is it a big gap? Is it a small one? Thing number 2 is this pairing energy. So does cramping 2 electrons into the same orbital, that same region of space, with the accompanying electrostatic repulsion, these 2 negative electrons repelling each other, does that or does it not outweigh this promotion energy to put an electron in the higher orbital? What an interesting question. In this case, it does. So that electronic repulsion means the 4th electron goes in there. 5 and 6. So we fill up this orbital anyway. What then does this complex have in terms of its magnetic moment? I've given you a formula, the spin-only formula, for working out this parameter, mu effective. So the extent to which the sample is affected by a magnetic field. And this is the square root of n into n plus 2, where n is the number of unpaired electrons. So how many unpaired electrons do we have? Different colour here, yellow, we're going yellow. We've got 1, 2, 3, 4 unpaired electrons. So n is equal to 4. N plus 2 then is equal to 6. So you're going to put that into a calculator. Here we go. Gosh, I'm prepared. Square root of 4 lots of 6. 4.89. Oh gosh, I should probably round that up. Okay, so 3 significant figures. Off you go. 4.90 Bohr magnetons, my favourite unit. I really love Bohr magnetons. What a great answer. Have loads of marks. Have loads of marks. And be thinking about this subtle interplay. Where does the 4th electron go? Where does it go? Why does it go there? These are excellent questions to ask. Perhaps in the workshop when you turn up, when you attend. Who knows? Example B. A palladium complex. A palladium-2 complex. A palladium-2 complex with 4 ligands. How interesting. Is it tetrahedral? Or is it square planar? it's square planar. So the heavier metal is bigger, it allows more space for the ligands around it, and this steric freedom allows the complex to adopt a non-VSEPR shape. So you would never see a square planar. Oh, is that true? You'd be surprised, I think, at a square planar complex in the P block. Finding the D block in the D block for transition metals having a D8 configuration is relatively common. Relatively common. Why is that? Well, let's look at the ligand field splitting. Some argument about the precise ordering of those bottom orbitals. But how do you fill up 4 electrons? Sorry, 4 electrons, 8 electrons. First electron, second electron. I would say probably 3rd, 4th, 5th, 6th, 7th, and then 8th. But the precise ordering there would be quite subtle. The main point is that you definitely do not fill up this dx squared minus y squared orbital. This is very high energy, you do not fill that up. In terms of the spin-only formula then, you have a lovely situation where there are no unpaired electrons. So the effective magnetic moment is 0. You can put the ball magnetons if you like, but I think 0 is the only time you could ever ignore units. There are no units of 0. D8 square planar. I think this is worth knowing. I think this is worth having as a fact in your head. That D8 complexes are typically associated with square planar geometries.